Cross entropy loss is the standard loss function for all machine learning classification tasks. In this video, we will see what is the intuition and math behind the cross entropy loss, why we use the concepts of entropy and cross entropy from the information theory, and why it is also referred to as the log loss. So let's get started. Let's first take a simple example of a binary classification. Let's say we have 10 points which can be either red or green, and each point has only one feature x. We want to build a classifier which will classify these points into red and green. Specifically, we want the classifier to predict the probability of the green class. That is, if the point belongs to a green class, we want its probability close to 1. Similarly, if the point is red, we want its probability close to 0. Once the classifier is trained, it predicts the probabilities as shown here. Here the green bars shows the predicted probability of the green class, and since we have only two classes, the probability of the red class would be 1 minus probability of the green class as shown here. Let's bring down the hanging bars, and this is what we have. We can see that there are two bad predictions here. It is bad because the predicted probability of the corresponding true class is much less than 0.5. We now want to compute a quantity called loss which will penalize these bad predictions. That is, if the probability of a green point is low, say 0.01, we want to penalize it more, and conversely, if that probability is close to 1, the penalty should be very low. And the same thing applies for the red point as well. The negative of the log function comes to our rescue. As we can see from the figure on the right, the negative log of a value close to 0 is much higher, and the negative log of value close to 1 is closer to 0. And this is exactly what we needed. Now let's see how we can use this in our case. The choice of negative log is not random, and we will see why later in this video. Applying negative log function, we have this. We can see that the two bad predictions are now given a higher penalty, and if we take a mean of all these values, we obtain what is called the cross entropy loss. Since we have only two classes, it is also referred to as binary cross entropy loss, and since we use log function, it is sometimes also referred to as the log loss. Now let's dive into the math. The equation of this loss function can be written as shown here, where n is the number of samples, yi is the label for ith sample, which is 1 for class 1 and 0 for class 0, and pi is the predicted class 1 probability for the ith sample. In our previous example, class 1 refers to the green class and class 0 refers to the red class. Now let's try to understand this equation by breaking it into parts. Let's first ignore the summation term. For class 1, yi equals 1 and 1 minus yi is 0. So what we are left with is just minus log of pi. Similarly, for class 0, we have only this term, which is minus log of 1 minus pi, where 1 minus pi is the predicted class 0 probability. So we can see that this exactly matches with our previous discussion of using minus log of probabilities for calculating the loss. But what is its relation to entropy and cross entropy? Let's see that now. If you like this content till now, do press the like and subscribe button to get more such videos. Okay, so coming back to the video. From information theory, we know that entropy is a measure of uncertainty associated with a given distribution Q of x. The equation is as shown here, where capital C is the set of all possible classes. For our example, this will break down as follows. Since we have only two classes, we have only two terms inside the summation. Let's understand it a little more. The distribution of green and red point is as shown in this table. That is, q of x equals green is 1 and q of x equals red is equal to 0 for the green point and vice versa for the red point. If we try to use these values in the above equation, we have the entropy of green point as 0 and similarly the entropy of red point is 0. So what this basically means is that since we surely know the green point is green and the red point is red, the uncertainty or the entropy is 0. But the classifier does not know the true distribution q of x. If this information was known, we would not be training the classifier in the first place, right? Since q of x is unknown, the classifier tries to approximate it using another distribution p of x. So if we replace q by p inside the log, we have what is called the cross entropy. That is, the entropy computed in this way is referred to as the cross entropy. We can generalize it for C classes and we have the equation as shown here. Notice that the q in the previous equation is replaced by p. The closer the approximated distribution p of x to the true distribution q of x for a particular point, the lower is the cross entropy. In fact, this difference between cross entropy and entropy is quantified using what is called KL divergence. Let's bring back both the equations. The top equation is the equation of the entropy and the bottom one is the equation of cross entropy. Notice that the only difference between them is that q is replaced by p inside the log function in the case of cross entropy. KL divergence is a measure of dissimilarity between two distributions. It is basically the difference between the cross entropy and the entropy. The closer the approximated distribution to the true distribution, the lower is the KL divergence and hence lower is the cross entropy. Coming back to our example, for point I, we compute the cross entropy as follows. It must be pretty clear by now that we can replace P of x equals red by 1 minus P of x equals green. Similarly, we know that we can replace q of x equals red by 1 minus q of x equals green. We can simplify this equation further and rewrite it as shown here, where yi is the label for point I and pi is the predicted class 1 probability for the ith sample. We compute this cross entropy for all the n points and take an average, where n is the number of samples. This is exactly the same loss function which we obtained earlier. Hence, this loss gets its name cross entropy loss. Since it is binary classification, it is also referred to as binary cross entropy loss. We can also generalize it for the multi-class case, and for the multi-class case, it is simply referred to as the cross entropy loss. The equation of multi-class case is as shown here. Here, n is the number of samples, capital C is the number of classes, Yij is the indicator function which is 1 when the ith sample belongs to class J and Pij is the predicted probability of class J for the ith sample. You can take a moment here and try to relate it with the binary case by putting C equals 2. Let's try to understand this with a simple example for the multi-class case. Let's say we have 3 output classes and we have 4 samples and the probabilities predicted by classifier is as shown in this table. The inner summation in the above equation basically boils down to these values for this example. And If we take the mean of all these values, we get the cross entropy loss. So that was all for this video. I hope you understood the concepts and the math behind the cross entropy loss and why we use the concepts of entropy and cross entropy from information theory, and also why we refer to it as log loss. If this video was informative, do press the like and subscribe button for more such videos. Thank you very much for watching.